This is the fourth session of writing a Lisp in Python. So I'm going to set up the environment like every other session. Okay, so now I've written a to-do file of every idea I had for what to do next. So last time we finished the some more built-in Lisp functions to manipulate Lisp values. We finished the recursive descent parser, and if we run the parse file, we have a script that a Lisp script that is read by the parser, and each value is parsed and represented as a pre-printed value. I just noticed that this symbol and this string have the same representation, and they shouldn't have, because strings are represented with quotes. So I think the problem comes from the inspect function. Yes, so I just have to do this, and now strings are represented as string literals. So the next thing I want to start is the interpreter, and for the interpreter we need to implement the eval function, and so we need to compute Lisp expressions, expand macros, lookup symbols, and implement the eval function. In this Lisp, I have something that I want to do, which is not frequently done in other Lisps. So if I run, for example, this, so if I run a compiled Lisp, usually the axioms of the language, like if or quote, cannot be bootstrapped. There are axioms of the language, but in this implementation, I want core functions like quote to be a special kind of function that can be implemented in Lisp or in Python. And the reason this is possible is because this is an interpreter and not a compiler. So if I write this or in a compiled Lisp, the Lisp runtime will return a symbol, and the quote function is not a function because the parameter is never evaluated. If I want to define my own function, like f, for example, and I run this code, x is going to be evaluated. So I'm not going to get the symbol x. I'm going to get in f the value of the x variable, or an error if x is undefined. And if I try to define a macro called g, the x symbol is going to be sent as a symbol to G, but when it is returned, the code is going to be evaluated. So I can't. So even I can't return. I can't just return the parameter because the content of the thing that is returned by G is going to be evaluated. So in command Lisp, for example, I could write this, and if I try to return x, I'm still going to get an undefined variable error, or the value of x. And if I want to, even if I wanted to do this, I wouldn't get the behavior of quote, because I would get if I run this, for example, I would still get the x symbol instead of the symbol inside x that without being evaluated. So in functions, if I write a usual function, parameters are evaluated before calling the function. If I write a macro, the parameters are not evaluated, but the result of the macro is evaluated. So the evaluation happens after computing the macro. And in axioms like this one, like end, the results and the parameters do not have to be evaluated. In the case of end, for example, if I write end false true or nil t in command Lisp, this will never get evaluated because end has evaluated nil and decided that since nil is not true, the other parameters do not need to be evaluated and will not be evaluated. If I want to write if, for example, x is a condition, so it's always going to be evaluated, but y is not going to be evaluated because if x is false, it is nil, and z is never going to be evaluated if x is true. So I want to be able to implement custom evaluation rules for functions, and the model that I want to implement is that every function, a runtime function object in this interpreted Lisp, can have 3 evaluation modes. Before evaluation, so the evaluation can happen before the expression. So x is going to be evaluated before f is computed. The eval can happen after, so j is called first, jx is called first, and then the result is being evaluated, or simply no evaluation. So in the case of nil, or in the case of if and end, it's the special axiom that is responsible for deciding when to evaluate something or not. This will allow me to define most built-ins like and, or, if, even functions like lambda or define with custom evaluation rules without modifying the interpreter itself. So in order to implement this, I will use the data types that I defined in this file. So I have defined 3 types. A function type, which is a generic function that can be called from Lisp. A native function type, which are for Python, which is a wrapper for Python functions. Yeah, I started the recording. And Lisp function type, which is for functions defined in Lisp, which are represented with a list of parameters and the body of the function. And any of these 2 functions can can use custom evaluation rules. There is no macro type. Everything is going to be defined in this type. So in here I'm going to define a native function which is going to use a Python function and return a value, a Lisp value, which is a wrapper around the Python function. We have Lisp functions which receive a parameter list and a body. And the native function constructor is not going to return a native function type, it's going to return a function. So I'm going to import these types. And when I want to create an object, I have to specify the type of the Lisp object. And I'm not going to create a native function, I'm going to create a function which is a wrapper around a native function. And I'm going to use the same pattern here. So the function type is a wrapper over another more specific function type. But in the case of Lisp functions, a Lisp function is going to be represented as a const cell. So this is a very simplistic representation. If I define a function in Common Lisp, for example, I have the name of the function, which is defined in the symbol table, not in the function itself. I have the list of parameters with potentially modifiers for special values. And I have a list of expressions which are evaluated one after the other, and this is the body of the function. So I'm not going to implement this, I am just going to implement a very simplistic, very simple list of parameter names, and I'm going to add a special variable which comes from the inspiration comes from JavaScript, which is not a great language, but so the idea is that every function can use the parameters special value, which is a linked list of all the parameters specified. So even if I don't declare y, sorry, if I don't declare y, I can't use it, but the value of the second parameter, so 3 in this case, is going to be here. And I'm going to use this special parameter value in order to implement parsing of more complex parameter chains. So for example, in Scheme or Guile, I can define named parameters, or in Common Lisp 2, I can define named parameters with symbols, with keywords, sorry, and the parsing of these parameters is implemented as part of the function definition functions. So in the case of Common Lisp, we define functions with defn, and defn is responsible for parsing special syntax like this. And in the end, everything is compiled to a function with a list of parameters. So I'm going to keep a simple arg list as part of the function definition, and not something more complex. Everything is going to be built from the parameter special value. So this is these functions are constructors for Lisp functions, which should be called in Lisp from the interpreter. But I'm also going to add the evaluation rules. So before eval, after eval, and no eval. For this values, I'm going to make them part of the function type. So for example, I could use this. I could concatenate the execution mode, whether it's before evaluating or after evaluating or without evaluation, and the low-level function, which can be a native or a Lisp function type. I need to refactor this code, especially the indentation. And for this values, I'm going to use keywords, not symbols. So I need to implement keywords. And keywords in Lisp they work almost the same way as symbols. So I'm going to use this as a template, but the exact rules of evaluation are not the same. If I try to evaluate a symbol in Lisp like this, I'm going to get the value of the x variable. But if I try to evaluate this symbol, I'm going to get the same keyword. If I try to evaluate this keyword, I'm going to get the keyword itself. So keywords are kind of like other data types, integers, strings, or whatever. They evaluate to themselves. They are not used as a metaprogramming feature, but they can be used to represent keywords, like for keyword arguments in functions with variable parameters, or as a name for in this case or as a special token for representing the execution mode of the function. this is everything that's important for keywords. If I write the same keyword in two different places, they are going to be considered equal, and the keywords are going to be considered equal, and there is no other specific operation, except maybe converting them to casting them to strings in order to manipulate them. My Neovim crashed when I tried to use the AI. I think my configuration is broken because it's not the first time. Yeah, my configuration is broken. So I'm going to define the keywords I want to use here. And that's it. I need to import the keyword constructor. Okay, and I need to rewrite this to be more a bit easier to read. So this is the wrapper over the native function, and this is execution mode wrapped over the native function. I'm just going to return directly the value. And I'm going to add an optional parameter, which is going to be by default what is needed for a function. So if I want to have a function, the parameters are going to be evaluated before the function. So the execution is happens after the evaluation. This is not very. It can be confusing because I'm always saying evaluating before computing, but here it's when the evaluation happens, when the execution happens. So the execution happens after the evaluation of parameters. In the case of macros, execution happens before evaluating the result of the macro. And in case of axioms, the evaluation is manual, so there is no automatic evaluation. Here, now I'm going to do the same for this here. And by default, everything is going to be a function, unless I explicitly want the evaluation to happen after or never. Okay, so now if I try to parse keywords, for example, currently I can't, because there is no syntax in the parser, so I can't test that the keywords work or the functions. This is a recursive descent parser. So if I implemented the keyword parsing in the tokenizer, I could just have this special case, and I would have exactly the same parsing code. This code is very ugly, but it's generated by AI, so I didn't really care when I wrote it. I should probably have wrap this in a metadata object, for example, to reduce these 4 lines to a single line. This case will not happen unless I add a special state in the state machine to parse keywords, and I don't want to implement this because it will be I don't want to add complexity to this state machine. I would prefer waiting until I have something. I have a bootstrapped interpreter. So in the meantime, I'm not going to add a special syntax for keywords. In Lisp, like for example Common Lisp, keywords are written this way. It's a special syntax. In this language, instead of having a special syntax, I'm going to cast from strings. So this is going to be a constructor for keywords in the Lisp runtime. I can remove this, and I'm going to start writing the interpreter. So in the interpreter we have there is another thing that I need to implement before the interpreter. It's the scopes for variable scopes. So the main functions of the interpreter will be the lookup function, which works in an environment and tries to resolve a symbol to the value of the variable. We also need the compute function which is going to evaluate recursively all the members of a function. So for example, if I have if I have this expression I need to get the function with a lookup, because I'm going to write f as a symbol in Lisp, and I need to resolve this. So func is going to be a function, and a function object that is resolved with the lookup function. And then the parameters a, b, and c are going to be evaluated in the environment. Same for b and c. And then I need to if assuming that f is a Lisp function, we know that f is a pair of an argument list, of a parameter list, and a body. So I'm going to for each expression in the body, I need to evaluate the expression after setting a, b, and c in an environment. So I need to create a new environment that inherits from the parent environment. Define that for the a symbol, I have the value of a for every argument which I know because of the arg list. I'm going to bind the name of the symbol in the arg list to the value of the first parameter, and I'm going to do this for each argument. And then I'm going to evaluate every expression in the body of the function. So for example, if my f function is defined like this, I need to evaluate this in the local environment, which is defined with this function. I'm going to also with this local environment that inherits from the parent environment, I can define other values. For example, I could create a counter, and then I'm going to increment the counter by x before returning the value of the counter. I could use a function like this, for example. And in this case, counter is part of the parent scope. So this could be part of a block somewhere in a more complex function. And if I define this and then define this function, so this current code does not allow local lexical scoping of variables. So if I want to define in a function let's imagine that this works. So if I define a function which defines a local variable with the let, for example, and then I return the variable, so I could do this with a lambda, for example. yeah, this code is better. So let's say I have a function that creates a local variable and then creates a lambda that refers to this variable and returns the variable. Then I need to create this variable in a local environment before executing this expression, and I need this environment to be part of the function, which is not the case currently, but I need this to be a part of the function. So this is called a closure. So the idea is that this variable, if I try to create a counter, I could use this counter and in this line J has already finished executing, so this code is over, but this variable has to persist as part of this function in order to dynamically create new functions depending on their local environment. So this feature is not part of the previous implementation of this project, so I need to implement this this time. And this code this code does what is called dynamic scoping. Scoping, yes. And this means in practice is that if I define a local variable before calling a function, the code of the function is going to be modified. So if I define a function that returns x here, and x is not defined, if I try to call f, in most languages we expect f to fail because x is not defined. But if I do a local definition in dynamically in a language with dynamic scoping, this code will work and f will return 3. This is not what I want, but this is a behavior that exists, and some languages do it. And Common Lisp, for example, can do both. So in Common Lisp, usually it's with functions like with context manager, like for example a macro that will open a file, or function that will a macro that will open a file, and then I'm going to add my code. So I'm going to open a file in this is pseudocode, but the idea is that I open a file in write mode, and if I run this code in Common Lisp, well, the real function with the correct parameters, and I run print for anything, print is not going to print on the screen. Print is going to write in file.txt. Yeah. So this is what is possible with dynamic binding, because the output, the standard output of the program, is overridden by the output stream of file.txt. But this behavior is not what I want to implement. I do not need dynamic binding. I just want lexical binding. So this behavior. And in order to implement this behavior, I need to modify the function type, because every function defined in Lisp, not Python function, but Lisp functions, will need an environment they will need to make environment their current local environment as part of their definition. I'm just checking that I can create a list. No, I can't. So I'm going to define a function as a list of 3 elements, and an argument list, a body, and an environment. And I want to implement a function for creating lists from Python, from a list of Python values. I don't think this name is available because it's a built-in, and Python prevents overriding built-ins. So I'm going to name this function makeList, and for every parameter in the arguments, I'm going to prepend to add at the beginning the argument to the result, and I'm going to return the reversed list, because if I don't reverse it, the first parameter is going to end up at the end of the list. So I'm going to use this function here. And in here I'm going to use this variable. So I need to import makeList, and I need to test what we did here. I'm going to command this. I want to keep this as a reminder, because if I forget about it, I may use dynamic scoping instead. So this is pseudocode. It's not going to work, but I plan to make it work in the next sessions. This video is already quite long, so I did not really do anything here. I just implemented functions with the special quirk of this project, keywords, which I didn't test, and that's it. That's all we did. I'm just going to finish the hooks for implementing the interpreter. So this is this function is yeah. So about macros, this compute function will not only compute function expressions, it's also going to compute macros. So I just have to remove this code to... So in a function, parameters are evaluated before running the function, and compute currently evaluates the parameters. But if I remove it, I can evaluate parameters externally and reuse this compute function for macros. I also need a function that will expand all the code that is every block of code that is parsed before evaluation. So if I have, let's say I have this code, for example, the expand macro is going to be called on this entire block, and the job of this function is to parse this tree and find which function calls are macro calls. So if j is a macro, for example, this expand function will only replace j with this parameter by what the result of the macro is. So expand is going to call compute with the j function, the j macro defined in the environment, and this code will not be evaluated. Instead, expand is just going to return the result of j and replace it in this tree. And after expanding the block of code, I can evaluate it with proper function lookups or whatever. And the final function is the evaluation function. So if I try to evaluate something simple like 5 or any data type, I'm going to return the expression as it is. If I try to evaluate a symbol, I'm going to return I'm going to make a lookup with the lookup function and return the value of the variable, of the x variable. And if I receive a list, I will expand the macros and then recursively evaluate. So I'm going to expand the entire block, whatever is inside. So if C is a macro, for example, I'm going to expand it, and then I'm going to evaluate recursively by computing A after evaluating the parameters. So I'm going to evaluate recursively. So B is going to be evaluated and C is going to be evaluated. If A is a function, then I'm going to compute A, and then I'm maybe going to evaluate the results if A is a macro. So if I can implement these 4 functions in the environment type, because environment should be accessible from the Lisp runtime, so I need to implement it as a Lisp value. And then if I implement these 4 functions, I don't need to change anything after that on the interpreter. I can just implement things like quote or quasi quote as built-ins, because quote is just an is an axiom, and axioms are just functions in this language. So this is the entire interpreter, 4 functions. I just need to implement the environment before being able to do this, and I need to implement environment inheritance, which is just a way of keeping the symbols, the global symbols, in parent scopes while manipulating child scopes. So, for example, if my environment is a dictionary, I need to keep a special property like parent scope. Set to the parent environment. And that's how I plan to implement environments as a Python representation, but I need to make it into a Lisp data type. So for example, I could use hash tables, which is defined here, which I already knew would be useful for environments. That's why I kept it here. So for example, the array type, I removed it because I knew I wouldn't need it. But the hash table type, which is basically a dictionary, will be very useful for implementing environments, and that's why it's the last type that we haven't used yet. So all of these types have been used. These functions are. I already knew what I wanted to do with these types. So you can see now that these types are used. This one is used for function execution modes. This one is used for booleans and nil or none or whatever we will use later. Symbols and cells are used for lists and symbols. Lists and symbols, and that's it. We haven't used anything else, and we won't until we get a functional runtime that can be bootstrapped from Lisp. So in the next session we are going to implement environments and hopefully the beginning of the interpreter. This will take several sessions because every function is simple in itself, but every function is small but hard to understand properly and write correctly. So I'm going to spend more time on it.